Okay, good afternoon. So, any questions? Firstly, some of you haven't spoken with me about projects at all, so I think it's quite critical that you start doing it. So again, you can meet me after the class. I'll be around for a bit, and again tomorrow office hours. We are also going to be handing out a homework tomorrow. We are waiting for some, in previous versions of this course, I've used something called an auto-grader system. Kind of the idea is to make the grading of software that you write more predictable, as well as to ease the burden on us. So we have a backend server where you upload your program and then it kind of tests it out. Except that the students who were managing it and created that, they have all graduated, so we were trying to revive it. So that's the delay. That system itself actually was a project in this course some years ago. Anyway, so we'll be handing that out tomorrow. So if you haven't borrowed the embed, please do. So continuing on what we started last lecture, which is basically looking at how to do scheduling of tasks on a CPU so that timing constraints are met. And we had also looked at kind of different kind of timing constraints, but then by the time we came to scheduling, we were basically looking at one type of timing constraint, namely tasks are arriving and they have a deadline that is from the point they arrive, they have to finish by a certain time. And moreover, we were looking at tasks which are periodic, which is very typical of things like sensors and all, because we periodically sample them. So that whole framework does apply to lots of systems. One thing which we saw was that we could distill everything down to this notion of assigning priorities to processes. And rest of the operating system, really all it does is that any time it has to schedule, it's basically going to run the highest priority task which is ready to run, as in it's not waiting for a resource, it's sitting in that ready to run state. There may be other tasks which are blocked because they need a resource, or they are blocked because they're waiting for an event. So like a task which is processing sensor data, it will at some point say, I'm done, now read the sensor data. And at that stage, the underlying sort of driver software will go to the A to D converter or the sensor, and then it will find there is nothing there, and then it will have to wait. So instead of spinning on it, it basically lets the operating system put this task into a queue, and the OS will switch to some other task. So tasks may get blocked, and because they need a resource, it basically translates into their waiting for an event. And otherwise, they may be ready to run, except they may not have the CPU because there may be multiple tasks that need the CPU. So the whole scheduling game then boils down to the tasks which are ready to run, which one should I actually run? The notion that we came up with was that if we think of tasks having priorities, then all the OS will do is it will pick the highest priority task. And then the question became, how do we assign the priority? And then there are other issue that we touched upon, whether the whole system is preemptive or not. Namely, the currently running task, can we bump it off involuntarily or not? So more, you'll find kind of simpler operating systems to be non-preemptive, but that has the disadvantage that once a task grabs a CPU, then it can go amok and essentially stall the system. And besides that, it hurts the schedulability of the system, because that example I've cited often, a rare task comes, but it takes a long time to compute. So it will block the CPU for that time, and usually then you start splitting tasks, and also not very convenient for the programmer. The other thing which we saw last time was that the worst case for a task, intuitively speaking, is when it arrives at the same time as a copy of each one of the higher priority tasks that exist in my program, because then this task will have the maximum queuing delay, so it will have to kind of wait for it. And the third thing we saw through examples, not a formal proof, was this notion that assigning priorities according to frequency is optimum for set of tasks where tasks are all periodic and their deadline is less than their period, is equal to the period. So they have to finish before the next event for that task arrives. And this thing is called rate monotonic. So priorities are monotonic with the rate. And then the question becomes that if the operating system is given a set of tasks, how can it decide whether it is schedulable or not? And the basic approach was to do this kind of simulation. So you'll have a proposed priority assignment, probably rate monotonic because that's the best, and then the OS can kind of conduct a simulation like this. It will basically say everything arrived at t equal to 0 and let me see what will happen, and then will this task, will any of the tasks miss their deadlines. The problem with that is that if the tasks have widely disparate periods, particularly if the periods are relatively prime, then you are basically looking at something which is the product of all those periods, and that could be pretty large. So the simulation can take a long time. Now this is not an issue if you are doing all of this offline, but it certainly becomes an issue if in a runtime system the program says create this new task and the OS has to quickly decide whether to let it through or not. So a quicker tests are useful, and one of the quicker tests that we saw was based upon the insight that so we had this theorem someplace, let's see, that I calculate the overall utilization of the set of tasks, which is basically percentage of the CPU each task needs, to sum them up. And then this theorem basically says that if the overall utilization is less than a certain threshold, which is a function of the number of tasks, then the task set is schedulable, and otherwise it may be schedulable. And then you resort back to the test where you do the simulation. And then finally, I had shown that a more recent result, which basically says that if I am willing to make use of individual processor utilization, then I have a better formula. That is, many set of tasks which the previous formula will throw its hand, this one will give us an answer, a positive answer. So so this is obviously a little bit more complicated than the previous formula, but not really a whole lot. It's still addition and multiplication, so it can be done very rapidly. Now, with all of this, you still face the situation that the set of tasks are unclear whether they are schedulable or not, because this formula, the left hand side, turns out to be greater than 2. So now we still have to do the test. So this is where we have to come up with an algorithm which kind of essentially does the equivalent of that simulation we were talking about, right? So I'm basically going to walk you through how to do that. So imagine that I think in terms of a task, an event for a task arrive, and when will this task finish? So that gap is the response time, right, from the arrival to actual completion. And what we want is this response time to be less than the deadline, because our deadlines are all relative deadlines. Now, one thing we can say for sure is that this response time will at least be equal to the computation time. If this task needs 1 second of CPU, then obviously I cannot finish it in less than 1 second time. So for the highest priority task, which will always get to use the CPU, the response time would simply be C, right? Because whenever it arrives, it has the priority, bumps up everything, and its response time is C. So that's straightforward. For lower priority tasks, the challenge is that we also have to worry about the interference from the higher priority tasks, right? Because they may arrive and grab the CPU. So the response time of an arbitrary task will therefore be its own computation time plus the interference it sees from all the other tasks that are higher priority, right? So the formula kind of looks like this. So now let's look at if we can expand this interference term. So the interference, so consider some task I and consider some arbitrary task j, which is higher priority. So what would be the interference that this task will see? So let's assume somehow we know magically that we know r, the response time of the current task, right? That's exactly what we're trying to calculate. But let's say for a given r, the number of time the higher priority task will arrive is going to be R sub I divided by T sub j, which is the period of the high priority task, and taking the ceiling because we are going to look at the critical instant, so there is a task which arrives right at the beginning. So there will be the higher priority task will arrive at least k times. And since it's higher priority, each one of them will get the CPU, and therefore it will take CPU time, the corresponding CPU time. So the total interference from the jth task which is from the set of higher priority tasks, is Ri sub Tj ceiling multiplied by CPU. Right? So overall computation. And now we can look at the set of all higher priority tasks and do the same thing, and that would be the interference. Now, of course, the challenge out here is that I'm trying to compute R sub I, and this interference itself is a function of R sub I. So what we have is a fixed point equation. R sub I is equal to task's own computation time plus an interference term, which is a function of R sub I. So common way of solving these highly nonlinear fixed point things is to basically do it iteratively. You start with some reasonable value of R sub I. So reasonable value could simply be R sub I is C sub I. And then you will iterate, and every iteration R sub I will only increase, right? Because this solution term is also positive. So I'm going to start with R sub I equal to C sub I, and then as I iterate, this value will increase, and one of two things will happen. It will either converge, or it will exceed the deadline that I have. If the moment it exceeds the deadline, I can stop because the deadline is violated, and if it converges prior to that, I'm good to go. So the whole thing then boils down to is that for each task, you have to solve this iterative equation, and kind of the next slide basically just has a code version of it. So fairly straightforward. In effect, if you think about it, it's doing that simulation that I had in pictures in graphical form before, because it will still, the number of times you will iterate, the time it will take to converge can be quite large, but nevertheless this is a perfectly fine way of doing it. There are other ways of thinking and formulating these things, but they all boil down to doing looking at these timing constraints that over time, if I do the simulation, is there a violation or not? Using something like this, then you can use it as part of a system design framework where you can begin to answer these kind of questions like, I have this set of tasks, I have this proposed CPU, will any of the tasks miss the deadline? Then one of two possibilities. One is, something misses a deadline. So the next question you'll ask is, okay, so how much faster CPU should I use, or how much should be the frequency of the higher CPU? Alternatively, if it turns out you're not missing deadline, then you could ask, can I slow down the CPU, or can I use a slower CPU, right? I mean, either reduce the frequency or just pick a different, cheaper CPU which is slower. So once you have this basic schedulability analysis, all those kind of questions become feasible, and you can optimize for things. So there are tools which sort of incorporate similar analysis. The final bit is that this basic framework also continues to work when deadlines are less than the period. So remember, thus far, this whole rate monotonic and all was for the case where deadline of every task was equal to the period of that corresponding task. But even for the case where deadline is less than the period, the same system works, except that instead of rate monotonic, it becomes deadline monotonic. Okay, so for example, I may have video frames arriving at every 30 millisecond, but the relative deadline may be only 10 millisecond, because I don't want to give the whole 10 millisecond because it will cause perceptual problems. So so I have 10 millisecond, in which case I will use 10 millisecond to as when deciding what priorities to give, and not the 30 millisecond. So so the generalization of rate monotonic, therefore, in that case, is deadline monotonic. That is, you take the relative deadlines and then assign priorities in that order. Again, remember, deadlines are decided by the environment, so to say. Period is a bit more complicated. Part of it is a function of your system, like what sampling rate your sensor is working and all, but that in turn is dictated by the application requirement. Like for example, if you're sampling a sensor, then you have to make sure that you're sampling it fast enough. The whole Nyquist rate and all that. You have seen in other courses, right? So again, that is also a computation, is dictated by the application. The only thing really under your control at the end of the day is computation time, because you can always affect the computation time over a large range by changing the frequency or by picking a faster processing engine, okay, and then kind of do these kind of games with scheduling. So what this example is showing is there is again a bunch of tasks, periods, their deadlines. If I were to do priority assignment according to the rate monotonic, then in that case I would have given the highest priority to the most frequent task, which would be task 3, which has the smallest period. But on the other hand, if I look at the deadlines and notice each one of these deadlines is still less than or equal to the period, I would be giving task 1 the highest priority. So that's the only thing that changes. And then back in our algorithm, you stop that iteration process whenever you hit the deadline which you are given, as opposed to the period. So again, basically very simple generalization of that basic framework. Okay, so now this stuff works, remember, with all the assumptions that we had made thus far, right? I mean, firstly, we made some unrealistic assumptions, but that we knew things like the computation time. Okay, that in itself, as there was some discussion last time, that in itself can be a challenging problem. Knowing deadlines and periods is kind of more of a system specification thing. But then there are a whole bunch of other things we assume. We assume that these tasks don't talk to each other. No sharing of resources. It's not terribly interesting. Any real system would have some interaction. We also assume that all this operating system magic of moving tasks and all doesn't cost anything, but even that does. So imagine two different scheduling, two different priority assignment. One of them results in a lot of swapping of tasks, a lot of movement of which task is running on the CPU, and the other one doesn't. Then if each one of those switches takes some time, then I'm wasting more compute horsepower if there are more context switches happening, more switching of processes happening. So then finally, it could also be that one scheduling algorithm gives me more opportunities to put the processor to sleep and save power, or maybe lets me run things on a slower speed than otherwise, because it may have more, it utilizes the process. It has more laxity in the system. So there are other criterion which can come into play, which can make one assignment of priorities better than the other one. Usually when you look at the spec sheet of these real-time operating systems, they usually talk about what the overhead is for them to switch, how long a time they disable interrupts. There are all sorts of numbers they throw out because they directly play into affecting the schedulability. If given to operating system, if one of them locks out the interrupts a lot more, or has a more inefficient way of switching between tasks, then it will cause more problems. The other thing is this: none of what we talked about is applicable to when deadlines are greater than the period. That is, if there is pipelining. And finally, we also assumed that there was a single CPU. So there are, to apply these things in real life, all of these things have to be taken care of. Now that's where the theory becomes either super complicated or doesn't exist. But some of the complications that arise, I've sort of tried to summarize out here, and then the next slide set kind of picks on some of these. So some issues that come up, one is that purely from a timing perspective, what we found is that assigning priorities according to time is the optimum way. But there is a consequence of this. Let's say, for whatever reason, the processor comes under load. Maybe the hardware throttles it down because there is too much heating happening and all. So if that happens, which task do you think will start missing the deadline? the one which are lower priority, right? Because they are the operating. But lower priority is strictly, in our framework, is strictly a property of timing. I may have a task which is less frequent, but it is more critical. And so this is where kind of these two different notions of priorities are in conflict, right? I mean, that one notion of priority is purely driven by time, but the other notion of priority is one which is about the importance. That is, if something has to fail, I would rather a less important task fail and not the one which is protecting my system. So that's one issue. Another issue is we kind of have this very idealized notion of things being periodic. In reality, nothing is perfectly periodic. And in particular, when data is coming from over the network, it's going to see a lot of jitter. So now you have two ways to handle it. One is, if something has a lot of jitter, then we put a buffer there, right, to smooth out the delay so that so we'll basically put a buffer, add some fixed amount of delay, but then that eats into a latency budget, right? So not a great idea potentially, or account for this jitter. Then thirdly, no system is perfectly periodic, as in not all the tasks are periodic. There's always going to be some tasks which are truly asynchronous. For example, the crash prevention task and all, I mean, they may these things may get triggered only when some event happens outside. So that's an issue as well. Then there are tasks which lock out the CPU. So it's very common that we to do something, so that to do things where we don't want anyone else to interfere with the task. A common way for operating system or for the task to do it is to disable the interrupts, because if we disable the interrupts, then nothing else can happen, even the OS cannot kick in. So locking out of interrupts begin to hurt us. I already talked about tasks with deadlines greater than the period. The challenge there is that if the allowable deadline is greater than the period, then I have the possibility that a new copy of the task may arrive and I'm still working with the old copy. So two instances may exist simultaneously, and that raises a bunch of issues there. Then processor power management. We talked about earlier that we can shut down things and we can change voltage frequency and all. How do they interact with our scheduling, right? Because if I'm going to shut down, when do I shut down? If I'm going to change the frequency, what's a good strategy to change frequency? And finally, if you're doing these things across multiple processors, either multiple processors on the same chip or multiple computers on a network, right? All these kind of issues come into play, and some of these things can be handled in the sense that the basic model that I presented can be extended with additional terms to incorporate issues, and the others you just don't know how to do it. And in those cases, you are probably going to do lots of simulations, Monte Carlo simulations and all, to kind of get a sense of what is happening. But at least this starts giving you a basic framework to think about. Yeah, question.
So what would be a problem, assuming that you're allowed to have a deadline greater than period for some tasks, what would be the problem with that?
Okay. So first problem that happens is that imagine each instance of these, this function which is handling the task, it interacts with some data structure. Okay, so now this other task comes in, so you have to make sure that there is no there is no problem occurring if both of them start running, or perhaps even if they start running out of order. So that's easy to do. Then also, oftentimes these tasks have local variables, local state, and these functions are not designed to be active simultaneously. So there's a term in software called reentrant functions. So reentrant functions are functions which do not have any state in them, so that you can enter them again and again, potentially in parallel from your program. Whereas if a function has some local state, some variables that it stores, some memory, then that can create complication, because that memory is in effect shared across different calls of the function. So reentrant code is very important to this thing. So that's another one. The third thing is that, and that's more of a schedulability thing. That is, for the other two cases, equal to deadline and less than deadline, we have the deadline monotonic and rate monotonic theory. For deadline greater than period, there is no theory. That is, it's the only way for you to come up with a possible priority assignment is to do exhaustive search. That is, you try out all possible combination of priorities, so whatever, factorial n. Okay, so that's the final bit which complicates things at this stage. So so to declare that this thing is not schedulable, you will basically have to try through all combinations. So yeah, so those are kind of the issues that come up here. Any questions on this? Okay, so let's look at some of these more sort of issues, that more advanced issues which kind of come up when we do about these things. So the same slide. So let's go after this. The first issue I want to talk a bit about is this whole notion of transient overload. So we design these systems, we deploy them, but and our model is thus far in the theoretical side was simply that the CPU has some speed. So C1 through Cn are fixed. Now one of two things may happen, and so C's are fixed, and the CPU capacity is fixed. That's why we were able to talk about U less than equal to 1. Now two things happen in real life. One is CPU capacity can go down, and that may simply happen because some other background task may start coming in. Like for example, even trivial stuff like there's a keyboard and the user starts hitting the keyboard too much. Okay, so that's calling the interrupt handlers, and it's eating into the time budget, right? So that's one. The other issue that comes up is if we start changing the frequencies and all because of thermal events, again the speed and computation time change. Finally, our estimate for computation time may simply be wrong. Maybe there are some data conditions under which we didn't encounter. I talked about last time that how floating point arithmetic, there are certain numbers and all that can cause inordinate amount of delay because they trap into software and are then handled in software. So if it so happens that you assume some workload and in reality it kind of was some values of C's and in reality they were different. Okay, so under this situation when there is transient overload, what we want to deal with is the issue that our notions of whether a task is critical or not and a task's priority don't always align. So in this particular example, we have the usual worst case execution time, we have an average case execution time. Also in this case, so what we're saying is that CIs are worst case, that's how we come up with a scheduling, but the average case are less, because what as typically happens. Then there are the periods, and now I have also added a column for criticality. So I'm basically saying that task number 3 is not critical, but according to the priorities that we give according to the periods, task 4, which is more critical than task 3, but will have the lower priority. So if things are going, so I can approach the settings. If I do the rate monotonic priority assignment and I use the peak values of CI, then you can convince yourself that this task set is not schedulable. Okay, but then at that stage you might say, could I design it so that the critical tasks continue to meet the deadline, but the non-critical task I allow it to miss some deadlines, okay, because it's not critical. Now I cannot simply implement it as is, because if I were to simply do a rate monotonic assignment, then task 4 will have less priority than task 3. So somehow I need to do something to align the two. So so what we don't want to do is that if there is any situation where either the execution time was more than what I thought, so maybe what I can do is I can schedule these things in terms of average computation time, which is schedulable. Pray that I will be close to the average, but sometimes the peak may happen and that may cause problems. Or again, I design the system assuming the other interference is going to be tiny, and then again hope for the best, but if something does happen, should have a graceful way of handling it. So what we want is critical tasks should all meet, and it turns out the critical tasks can work, but we have to make sure that the priorities kind of line. So one way you could say is following, okay, forget rate monotonic, let's try priority assignment according to importance. And if that works, great, but turns out in this particular case that doesn't work. And in general it won't work, because what may happen is I have an important task, but it's very infrequent, okay? And therefore it's so far off from, and then I have a very frequent but less safety critical task. So this is where one way to fool this whole scheduling framework is to start splitting the tasks. So what's happening out here is the following. So it's an even simpler example. I have two tasks. Task 1 has a period of 10, task 2 has a period of 14. Their deadlines are 10 and 13 respectively, and their computation times are 3.5 and 7. And if you look at this, then task 2 has a lower priority in the rate monotonic sense. But it is a critical task. So how can I transform this thing so that task 2 gets to have the higher priority? And the trick out here is that we split task 2. So what we do is we split task 2, let's say, into two halves. Part 1, part 2, okay? Now, part 2, and let's say I somehow magically able to split them into two equal halves, then each half will have a computation time of 3.5. Since I have two halves, they are going to arrive now more frequently. So the period goes down to 7. And the deadline now is going to be a trickier one to handle. Remember, my deadline was 13. My period is 7. So for alternative 1, my deadline is going to be 6. For 1, I can take all of 7, but for the other one, I have to take 6. So I have to take the worst case. So my deadline is going to be 6 here. So now I have split the task, changed it this way, and now task 2 has a higher priority. Remember, utilization is the same, the portion, so U remains the same. All I have done is I have changed, by splitting, I have a smaller, more frequent task with, that is correct. The gotcha in this whole thing is, can I do this splitting? So if I ask you split some piece of code, some function into two halves, what kind of issues come up?
Well, like the second task kind of think that the first task.
No, it's a single task, right? So it's just a function. So whenever the task comes function, now I have to split it into two halves. Half 1, part 1, part 2. How would you go around doing it? So the challenge comes here is, if you think about it, remember, just estimating how much time the code will take is hard enough. Now you're trying to find the precise point in the middle. There may be loops. Where do you stop in the loop, right? And tiny changes can affect these things and all. And here I'm only dealing with 2 parts. What if I asked you to divide the task into 5 parts? Far more complicated. So from a purely software engineering perspective, not a terribly good thing to do, but if you can pull off this the splitting, then great. One possibility is the task monitors its computation time, and when it has hit the halfway point, then it voluntarily gives up the CPU and schedules another copy which will start from where it left off. So through some sort of states and all, you could pull it off, and sometimes you don't have a choice. I mean, you will have to do these kind of games to achieve timing properties, basically. It turns out, if you kind of think about it a little bit carefully, if I'm allowed to chop tasks like this, right? I give you a task with a computation time of 100. If you let me chop it up into very tiny slices, okay, so it essentially becomes a chain, then I can always sufficiently split the tasks to make things schedulable, and the only thing I have to worry about then is that overall processor utilization is less than equal to 1, because essentially I can, by chopping, I can arbitrarily play with the priorities of the tasks. So there is another kind of result in the field, which is the following. If I have a set of tasks whose periods are harmonic with each other, that is, task 1's period is something, task 2 period is a multiple of task 1, task 3 like that. If I have periods in a harmonic manner, then again the schedulability boils down to u less than equal to 1. So there are certain special cases, like for example, maybe you can artificially mess with the period. You can change the system specification to make it more scheduling friendly. This is again kind of an example of the same genre, that by playing with the tasks, you could make the system schedulable. In the same vein, another reason why where complication comes in is sporadic tasks. So sporadic tasks are tasks which are outside our periodic framework. And so how do we kind of handle it? So a very common approach that is done is the following, that I will assume that I have a periodic task which is like a server. So essentially this is a very high priority virtual server that I'm going to create, and it's going to get the CPU, and what it will do is whenever it gets the CPU, it's going to go and check if any sporadic task is waiting in a queue, and then it handles it and then goes back. And it turns out that with this you can there is sufficient mathematical analysis that exists where you can now begin to say something about what's the deadline that what's the response time that a sporadic task will see. And there are smarter ways of organizing this, like for example, what may happen is within a particular period, the server may wake up, the server task may find that there is nothing, but then a sporadic task just arrives a little bit later. So there are concepts like you can move around the time allocation of the server. So like for example, in the time slot out here, the server woke up, didn't find anything, but then maybe the task arrived a little bit later, then you can recoup the time instead of entirely losing that time. So there are all sort of these things that exist. One of the challenge that very soon you begin to run into is kind of this concept of fairness. And there's no easy answer to these things. So let's imagine a user told me that he needs 10 seconds of CPU time every minute. Okay, so every minute I just go to him and say, okay, here is a CPU, and you run it, right? That's what's happening in a server task, except he's not ready to run because of whatever jitter and stuff like that, things haven't arrived. So he missed a turn. The question then becomes that, should I issue an IOU, or should I say, tough luck, we move on, you have lost this opportunity? And in most systems, you'll probably try to strike a balance, that is a little bit of an IOU, but you don't want the IOUs to build up, because then this user can just accumulate things and then cause deadline problems later on. So with these sporadic tasks and all, one has to kind of account for these kind of things. Sometimes these things happen naturally also. So let's imagine I have a wireless link, and there are a bunch of users, and I give them time slots. So time slot 1 is for user 1, time slot 2, user 2, and there is a periodic, they change periodically. But the wireless link suffers from noise. So let's say when it was your turn, I said, okay, go ahead and transmit, except lo and behold, at that time the wireless link flicked out. So even though I gave it a time, but the link was not usable. Equivalent of that would be, I gave you the CPU, and the CPU at that time started undergoing some thermal emergency, so you really didn't get. So in those cases, one has to be careful that just giving time on a resource is not equivalent to giving the resource, because if the resource is undergoing some sort of a state change, then one has to be careful about it also. So complications in these schemes really arise from all these kind of issues. What is fair across the users? How can I prioritize them? All those kind of come up. But these are some of the ideas that build up. A related one is, how do we handle uncertainty in execution time? So we saw a little bit of that just now. So tasks often have this highly variable execution time, highly data dependent execution time. So one image comes in and it may take 10 milliseconds to process it, and the other image comes in and it doesn't really have much, and it takes microseconds to process. So how can one handle these things? So the situation is basically this, that worst case execution time is a lot greater than the average case execution time. So one way is, you can say, fine, I'm still going to design my system for the worst case, but any unused time, I'm going to use it for some other purpose. Like, for example, I can run some other stuff, or maybe I can shut down the CPU and save on power. I could do those kind of things. But there is another version, and this is this topic has been around for the past 20 years, but in the recent few years it has gained a lot of prominence, and it's called approximate computing. And the reason it's gaining a lot of prominence is that these issues of execution time varying, either because of the data or because of the platform, are becoming much more prominent. In particular, as chips have shrunk, there is a high degree of dependence on environmental conditions and all that has begun to happen. So the execution time on a processor can vary considerably over time, from processor to processor. As the processor ages, all those kind of issues come up. So one way of thinking about approximate computing then is that a less precise result is okay if the alternative was to basically entirely miss the deadline. So we reframe the problem to say, okay, I have a deadline, I still want you to meet the deadline, but if you cannot do the high quality computation, then do a lower quality version of it. And there are many ways of structuring computation like this. Sometimes you can organize the computation in a manner where there is some sort of iterative loop, and each iteration is computing an extra bit. So like, the first iteration gives me the highest order bit, and the next iteration gives me the next order bit, and so on and so forth. So the more time I give this task, the more bits, a more accurate result it will produce, but if I can stop it anyway. So, and you'll find these things in many domains. A lot of problems are search problems. A lot of problems are signal processing type things, or kind of in machine learning context and all, where basically more computation time, it can hunt more. Think of like Google. You type a search query, it will put the first page very rapidly, but then it can still keep searching more. I mean, if it's a popular term, there are going to be a lot more things, or likewise hunting through a database. So a lot of computation could be organized in this manner, that it's inherently that you give it more time, it will give you a better quality result. Okay, so that is one approach, and if your algorithm is amenable to that, you could. And a lot of people have done things like thinking of standard computation in manners which let you do these things. So like, for example, think of like a neural network, right? I presented an input, it gives me a class. What if I were to design the neural network so that it gives me a result, and then a little bit later it gives me a better result, and a little bit later it gives me even better result, and so on and so forth. So could I structure it like that? Could I architect the neural net in a manner where more time gives a better result, which means it doesn't throw away the state. It's not as if I'm rerunning a totally different, more accurate network. I'm reusing the partial result, but at any stage, the partial result is still useful. Okay, or let's say, can I design a filter so that it produces the output signal most significant bit first, then the next one, then the next one, and so it gradually gives me a more accurate representation, but very early on I have a good representation there. Okay, so these are inherently elastic algorithms, they're called. Okay. The other alternative is that maybe I can have multiple versions of the algorithm. Okay, one which is higher accuracy, takes more time. The other is poorer accuracy, takes less time. So in that case, I have a precise version and an alternate version. Okay, and so no longer iterative, but really I have to make a choice between running one or the other. Okay, so again, precise version takes a lot of time, but these are variable times. So like for example, I know the worst case time for the precise version, but the average case is a lot less. And then for the alternate version, the less precise version, I have a lot smaller, lot shorter worst case time. So in the hope that I have a good piece of input, I will try the more precise version, but if I'm unlucky, then I'll miss the deadline. So how do you think we can make use of such alternate versions and still not miss the deadline? So again, the problem is I don't want to miss the deadline, but I'm willing to sacrifice on the quality, and obviously the goal is to maximize my average quality, right? So it's not acceptable that you simply say, I'm always going to run the least quality version. So how do you think you can approach this? So imagine you have a deadline of 10 seconds, let's say. Imagine you started running the high quality version, and it can take anywhere from, I don't know, let's say 2 seconds to 20 seconds, depending upon the data. And I have this less accurate version, which always takes 5 seconds. Okay, so just to keep simple. Could you think of a strategy where you can, as much as possible, run the high quality version? Yeah.
So, like on Windows PC, if you search for a file,
Say that again?
on a Windows PC, if you search for a file, first it displays you like the all like the results of a deep search are displayed like towards the end, and initially it just shows you all the results that can like require you.
Mm-hmm.
So I would like try to go for the low hanging fruit first.
No. So that is the first type, right? That's more of the elastic algorithm. Okay, it gives Google gives me the first page of search results very rapidly, and then does presumably even over a smaller data set and searches, and then in parallel is searching for all those other 20 pages or whatever it shows. But no, the problem specifically here is I have two versions of an algorithm. Okay, one is a high quality version, except that at times it can take more computation time than my deadline permits. And then I have a low quality version which will always fit. So a specific example I'd given was a high quality version takes anywhere from 2 to 20 seconds. I have a 10-second deadline, and the low quality version always takes 5 seconds. So can you think of a way to use both beneficially?
I can start with the high quality until I have 5 seconds left and then
Exactly, right? So that's the basic strategy. You start with the high quality one, you do an optimistic execution, and then but keep track, am I getting too close to deadline? If I am, you switch over to that backup one so that you do finish.
It is an essence sort of having the deadline.
Pardon me?
Sort of having the deadline.
Yeah, I mean it is basically saying that the deadline I am putting on the high quality task is my deadline minus the execution time of the low quality task, right? But that's not what you're going to present to the scheduler, right? I mean, to the scheduler, you're still, because remember, if you put too tight a deadline, the scheduler may say, hey, I can never run the high quality task. Its worst case execution time is 20. Okay, so so basically you have to switch to these kind of dynamic strategies here. So again, two approaches, right? One is design algorithms which are elastic, as in they have some structure that if I give them more time, they give me a better quality result. And thankfully, lots of things are like that, because deep down they do search or some numerical computation, which can always be structured, or often can be structured in this manner, right? And the other one is to have these alternate things, right? Okay, so I have, since I was doing the neural network example, so the analogy out here is I have two neural networks, one which gives me poorer quality results, but always very low amount of time, and the other one gives me high quality result, but the timing is highly variable. Okay, so how can I exploit that? Yeah.
Could you make a case for maybe pre-computing with the lower quality algorithm first?
Well, you can't because the data wasn't there,
Okay, so
right?
data
So there's no
arrives.
pre-computation possible. Data arrived, you have these choices of structure.
How about like taking the system state into account? So like if my system is currently being throttled, then there's no way I can do the.
Fair point. In fact, you could also, the other things you could do is maybe there is some structure to the computation time. Like for example, that that certain kind of data results in the higher computation time. So you can keep track, and maybe there's correlation in the data. Another thing which you could potentially exploit is that maybe after you looked at the data, then you can tell whether it's going to take long time or short time. Like I can very rapidly assess, is it a simple image or a complex image, and then switch. So these are all other ways you could also structure. Common example occurs in speech. Many speech processing algorithms, what they do is they look at the speech signal and they organize it as periods of silence and periods of what are called as talk spurts. So you have a packets arriving, and the packet may simply say silence, and there is nothing else, okay? Or the packet may say talk spurt, and here is a waveform. Only after you examine the header of the packet would you know what the execution time is going to be. Or another one, video compression, MPEG and all, right? The way they work is they send you these frames, video frames, which are like static images, but then in between, they send those once in a while, and in between they send you the delta. Okay, so kind of the motion that happened, only that.
Subtraction kind of?
Huh?
Like background subtraction?
Well, it's a lot more sophisticated, but intuitively, yes. I mean, basically, I may tell you that, this new frame is the same as the old frame, but this patch moved by this delta. Okay, so I could play these kind of games. So modern video coding is super smart. Okay, they basically figure out the background and they figure out the objects, and then they move the objects around. Okay, so those kind of things. Again, the computation time for a full frame is a lot more than these partial frames. So you could, after examining the packet, you could do it. So that's the other strategy. So correlation, examination of the packet, system state, these are all ways that things that you can incorporate. Yeah, and all of them, I mean, some of them unfortunately have a possibility of being wrong, so you still need some backup strategy. Fortunately, what also helps is that many of these applications, many of the real-time applications are elastic from the user perspective also, right? I mean, yeah, even your fancy 8K television, I mean, probably once in a while is going to have some blip and you won't even notice it, right? Maybe it will not render some pixels very accurately, and it's just one frame out of many. Yeah, most users won't even notice in that 30 frame per second barrage of frames that is coming. So you also make use of the fact that applications or whatever, the consumer of whatever you are producing is also perceptually limited. Okay, so you don't have to go out of your way. But on the other hand, there are certain situations where failure is just not acceptable, right? Whatever, high energy physics, people at CERN, these kind of things. I mean, you don't want to result in something missed or a bad discovery or US military, right? I mean, these kind of applications obviously tend to have different threshold of what is acceptable or not. So uncertainty in execution time gets handled this way. So this slide basically is what you kind of mentioned, which is I basically wait until the time until I'm kind of in this point of no return, right? That the only time I have left is my high accuracy task is still not finished, and I just have barely time left over to run the low accuracy task, so better run it. Okay, so that's what we will do. This slide is basically just talking about, like, for example, I give more cycles, it can produce additional bits of my result. Okay, so a lot of numerical computation, a lot of graph algorithms, a lot of database algorithms, they're kind of organized like this because they are basically deep down some search which is going on or some iteration which is going on. So how do we deal with these kind of systems, these approximate computing kind of thing? So here what we do is we switch our notion of computation time a little bit. Okay, so remember this our notion of what we are trying to achieve a little bit. So thus far our model was, if the task misses its deadline, it's catastrophic. If it meets its deadline, terrific. So it was almost like a binary reward, 1, 0, and we were trying to basically make sure that it's always 1. But now what we do is we change it into what is called as quality of service or reward. Okay, so essentially the idea is that if I give the task less than some threshold, then I get no reward. Okay, so this is kind of like the bare minimum that must happen. If I give the task more than O plus M resource, more than O plus M CPU time, then I'm at the point where benefits are saturated, right? I mean, so I'm showering more time at that task, doesn't improve anything. So almost any real algorithm will probably be some point of no return where it saturates. And in the middle, I'll have some sort of a monotonic function, right? I give it more time, it increases the reward, okay, utility, happiness, whatever you may want to call it. But basically, that's the model. That so essentially, you can think of it in economic terms, that the more resource I'm giving to this entity, it's able to produce more, but only up to a certain point, and there has to be something bare minimum that also has to be given. So so this problem in RTOS community originally was called IRIS, increased reward for increased service. But you will find variants of this problem in many different communities, in networking, in sort of high performance computing, and all. Often they go under the that they're called quality of service and all, but the basic goal is that I'm trying to maximize the utility, the reward, subject in some cases to that there should be some reward, not zero reward, because failure is not acceptable. So we bring that out somehow. So it turns out in this kind of model, one type of method, they have been studied quite a bit in economics, okay, because essentially this is a similar model. So a lot of ideas from economics get applied in this setting also, like how do I structure this thing and all, that's the question. How do I even know what this reward function is, right? How do we assess what the utility is if I increase the quality of the image being produced? So all these issues partly are serious one in themselves. So like for example, people do human subject studies, people do, or maybe look at just crude metrics like noise and all, okay, but usually in domains like video and audio, there are human subject studies done to see that this quality of image is rated, how is the image quality rated by the human users and all. Then from the world of economics, we also have tools which seek such optimization. So auctions, lotteries, all these kind of things are basically ways to optimize allocation of resources across a society. So people in the scheduling side have adopted all these kind of things, okay, so they basically have taken economic ideas and applied them to these kind of problems, because essentially the underlying framework is the same, really, okay, that resource and the utility you are kind of getting out of that. So there's a wealth of literature which in many domains which basically have looked this type of problem. Okay, so next topic is task with shared resources, but since it's almost 5 p.m., so let's take a 5-minute break and then we are going to pick that up.
Actually, you know, I just have a question here for which is a jerk, I will say. So basically, so justice words is like
Yeah.
We decided to choose one for the using the smartwatch to use as a mouse.
Okay. So did you reach out to the student, the mentor in that one?
Not yet. We want to just talk to you first, see how this project is feasible for us. And
Okay, sure. Tell me a little bit about your background. Like, I mean, have you done? So basically, okay. So one question is, what is it? What's the device that you are going to have in the hand, right? So there are 3 or 4 different possibilities that exist out there. So one is that there's a device that we often use and which the student who offered this project is very familiar with, which is from Ohio State University, but it basically gives us access to the underlying accelerometer, gyroscope, those kind of data. Okay, so the basic framework for getting the data out is there, and you kind of your starting point would be that imagine this thing is talking to your phone, and the programming basically happens in the phone. So one thing that you would need to have is the ability to program on the phone. Okay, do you guys use Android, iOS?
we actually don't have like the experience programming the phone.
You don't have experience programming.
Yes. Our thought is since we currently have the Hexware, and they have like embedded accelerometer and gyroscope, so I think we can just
You can use Hexaware.
Yes, we
Okay.
can take the data from those sensors and do the programming and data processing within the Hexware, and basically send the command out to either the PC or a phone. So
You could. One of the challenge that, yeah. So you could implement these things on Hexaware, absolutely. But remember, since the BLE link is pretty slow, so you can't really stream the data out. So the actual computation will need to happen on the Hexaware.
yeah, that's
Okay.
what we're
Yeah.
thinking. of.
Yeah. So you could train and then deploy. So Hexaware is perfectly fine too. Absolutely. In fact, again, that was the other platform I was going to suggest, and the third platform I was going to suggest was one of the smartwatches. Okay, so either Android or thing. So if you decide to go with one of these other options, we can give you the thing. If you decide to do with the Hexaware, then you already have the Hexaware. Okay. What you could also part of the thing out here would be that you'll have to train a model. So during that phase, you have to collect lots of data. Okay, this is going to be. Do you recall one group had done this project about the basketball shot quality? Do you recall that?
Basketball shot quality.
Yeah.
Is that mentioned in the?
No. There was a project which people had done around Hexaware. I'm basically mentioning them as prior projects. Okay, but in any case,
Is that group done in some like the hackathon?
they're done in my other course. But you have purchased Hexaware?
Yes, we have one.
You have one already. Okay. Yeah. So no, you can do it on Hexaware, and like I said, the challenge here is that how do you get the data on which to train, because Hexaware is not designed to extract a lot of data. Okay. So what I can give you is the following. I have tiny little board on which Hexaware plugs, and that board is still tiny enough that you can still kind of wear it and then collect the training data using that while being able to move your hands around and all. Okay, because it brings out the USB and everything. Okay, and then you can sort of do the training, and then you learn a model, and the idea would be to use a model which is simple enough to fit on Hexaware. So I also mentioned that ST Microelectronics, for example, has this AI tool also. So there are a bunch of low complexity ways of implementing different kind of classifiers and all that are floating around. ARM has also released a library, so you could use one of those.
Okay.
Okay.
We're gonna
Yeah.
do some research on that.
So why don't you go and talk to Vikrant?
Okay.
And tell him that you already have Hexaware. We can loan you additional Hexaware if you want, and yeah, go for it.
Oh, okay.
Okay.
Thank you. We'll talk to him.
Sure.
Thank you.
I didn't give the email addresses there, but you can always Google my lab's webpage and look at it. Yeah.
So if I get dropped out, because I'm assuming he's screwed. So hopefully nobody drops from the class. If there's a function drops it, it's just get cancelled. So there's that, and then there's just like the code part. Yeah, as in, it's not that fun, guys. It's the translate back here.
Okay, let's restart. So next thing I wanted to discuss is how do we deal with tasks that are not independent. So remember, that was kind of a big assumption we had made, and there are many ways in which tasks may depend upon each other. One is one task can send message to another task, right? So one task generates an event which the other task triggers on. That's a very common scenario. Like, for example, you may have a task which is handling sensor data, and maybe, let's say, it's collecting the sensor data into packets, and then the other task waits for that packet, right? So that's one situation. The other situation happens is when the tasks need to coordinate. Like, for example, maybe I have two tasks controlling two different robot arms, and I want the two to be choreographed in a particular manner, okay? And the third one is they're sharing resources. That is, there are some data structure or hardware resources, and they need to be shared, except that you can't just willy-nilly go and work on these resources, because these resources often have mutual exclusion constraints. That is, while one party is using the radio, the other party cannot, for example. So I'm going to focus on this third category for now. So basically, the tasks are interacting via these resources which they are sharing. And commonly, these are going to be sensors and network resources and things like that. And the problem that you face out here is that since the resources are mutually exclusive, so I need to lock them. So if a task starts using the display or the radio, it will lock it. If I didn't have a proper operating system, then I would probably lock it by disabling the interrupts. But alternatively, if your operating system, like Mbed OS and all, if they have things like semaphores and all, then you would use those. So now what's happening is this task, when it starts using, it locks the resource. The problem out here is that imagine a resource which is shared by a high priority task and a low priority task. And the low priority task needs the resource. It's running, it has a CPU, it needs a resource, it locks it. So firstly, I have to account for this effect for the high priority task. But also, all those tasks in the middle, which were not using this resource, they are also going to run into problems if I start, we'll see the way we deal with these things. So bottom line is that previously, when we talked about what the response time was, we only worried about the higher priority tasks. But now we also need to worry about the lower priority tasks. And shared resources just so pervasive that any system is going to have that. But fundamentally, if you don't do something about it, then the timing constraints get violated. And the phenomenon is called priority inversion. So it's a situation I was describing. Let's imagine T1 and T3 are couple of T1, T2, T3 are tasks. T1 and T3 share a resource. T1 has a higher priority, and T2 has intermediate priority. And now let's imagine what happens in the following. T3 locks the resource, so more precisely, locks the semaphore protecting that resource and starts using that resource. Then T1 becomes ready to run, and since it is the high priority task, so it will get the CPU. T1 now also tries to use the resource, except it will find that the resource is busy, so now T1 is blocked. So now what happens is T1 is blocked. Now T2 begins run. Now remember, T2 is also higher priority than T3, so it will get the CPU. So what's happening now is T2 gets the CPU, T3 is still pending, even though it is using that resource which T1 needs. So intuitively, what we want to accomplish at this stage perhaps is that temporarily T3, because it is blocking T1, which is a super high priority task, so T3 should inherit or somehow get the same privilege as T1, so that T2 doesn't lock it out, because it could be that T2 is very frequent and T3 may keep waiting forever, and as a consequence T1 will have a long wait. So so we have to structure these things, otherwise bad things will happen. T1, my high priority task, will actually see all this interference and may miss the deadline unless we are careful about it. So what would we prefer in this case? Like I said, what we would prefer is that T1, being the high priority task, should not have to wait any more time than what T3 would have taken to finish using the resource, right? So if T3 needed the resource for 1 second, then there is no reason T1, which is the highest priority task, should have to wait for more than a second, okay? And so we have to somehow arrange for that to happen so that T2 doesn't cause an unnecessary wait to T3 and thereby to T1. But as kind of I talked about, the way if you're not doing anything about it, if you're just running the rate monotonic stuff as it is, then T1 can see a very, very long amount of delay depending upon how frequent T2 is, okay? So duration of this priority inversion would be a function of task execution times and such, and it's actually no longer, I mean, unless we do something which we'll talk about, it's not just the amount of time T3 needed the resource for, okay? So T3 just needed it to send a packet out or message out, but because of this complication of T2 butting in, we basically have a problem. Now, this was the cause behind one of the episodes I had highlighted in the previous lecture as causing problems. So this was the Mars Pathfinder thing. So again, kind of what had happened was that into the mission, basically the rover started to reboot repeatedly. And the public version of it, or whatever, the newspaper version of it, was simply software glitches and all. But what was that glitch? So the glitch turned out to be a failure which was a result of this priority inversion. So these systems run real-time operating systems. They are doing in a small package a whole bunch of timing sensitive things. So what was happening was there was a high priority task, happens to be called BC dist, doesn't really matter. It was blocked by a low priority task which had grabbed the shared resource and then was being preempted by a medium priority task. So exactly the scenario kind of I laid out: T1, T3, T2. T1 was the critical task, T3 was the low priority task, and T2 was the intermediate task. In particular, T2 was some sort of a task which was involved in science, okay, as in collecting data and all, and they had not anticipated how much workload it would have correctly. It turned out that Mars was more interesting, so the sensors were finding more interesting stuff to analyze, so there was more load that was coming in which they hadn't anticipated. In any case, the classic situation would set in, and now meanwhile, since the high priority task, the scheduler task, BC dist, was high priority, so there was some guard against it missing the deadline. So in the system there was an even higher priority task which would examine that if BC dist, the one which we're worried about out here, was missing its deadline, and if it was missing its deadline, then it would reset the whole system, okay? So essentially we have the important task, and if the important task is missing the deadline, then an even more important task is the kind of the watchdog task is responsible for just restarting the system. So that's basically what was happening, that because this intermediate task was seeing a lot of interesting sensor events, so it was doing it, causing the low priority task to therefore be delayed while it had locked the resource, and therefore in turn the high priority task was missing its deadline, and in turn the system was being reset. So that was kind of the chain of events that was happening. So so this wasn't in, so apparently what had happened was that these episodes occurred rarely on Earth, but they were dismissed as like rare events, hardware problems, sort of not handled. So, but when it began to cause a lot of problems there, so they had a exact replica on Earth, and then they tried to replicate. So it turns out that the operating system they were using, something called VxWorks, as an industry strength RTOS, kind of one of the was a fairly dominant player until Linux kind of made a lot of inroads. Essentially, it turns out that it supported a feature whereby you could accomplish what I was describing, which is that low priority task which had locked the semaphore would temporarily get the high priority task. Now, you could do it in your program semaphore by semaphore. That they couldn't. Remember, I mean, this is sitting in Mars, and you have to reprogram the system over that long delay, low bandwidth link. But the operating system also had a global flag, and if you set the global flag, then all the semaphores behaved in this manner. So that's what they did from Earth, basically. That after they identified, they basically just made that one tiny little change, made all the semaphores, and that kind of saved the day for them. Like I said, the problem is that these things manifest themselves unpredictably. Remember, the occurrence of these things is also a function of the precise timing of the way the events are happening and all. So this is why simulation and just running the system multiple times doesn't really work. I mean, there are just way too many combinations, and you can easily miss them. Or even once in a when they do happen, the system crash, you have no idea what happened, because the ability to see under the hood that this was the issue, that level of instrumentation just isn't there in systems. So this is where analysis plays an important role, which is to the extent you can, you should also attempt to analyze the code to make sure that bad things won't happen. And this falls into that category, that it could be analyzed. Now, when, like I said, some of these things were happening just around the time that the theory for handling these issues was basically also being developed. Much of the work in the space happened at CMU around that time. So almost concurrently, kind of sort of a high visibility failure, and as kind of the theories were coming out. So so the challenge really is that if these problems do happen, it's very hard to distinguish them from umpteen other things, a glitchy cable, some noise, stuff like that. They are infrequent enough, unless it so happens that you're unlucky the way these guys were, and then sort of failure starts happening repeatedly. Okay, so how do we avoid, how do we deal with these things? So our problem is fundamentally, there are three aspects to it. There is a priority inversion problem, that is, we want to give high priority to that low task which has blocked the resource. But what really has happened in effect is that my high priority task, which needs the resource, effectively has the low priority now, right? Because it's blocked on that resource. Second thing, so we need to understand this blocking, because this blocking is causing an interference. So we need to add a term to our response time to capture that. And then finally, we need to find some mechanism so that that blocking time is not too long, because otherwise you may have repeated blocking, and also could we do something about it. So just to kind of run you through an example of kind of things which are done. So so what we have is a system with 4 tasks. They have the priorities which are shown. So L4 has the highest priority and L1 has the lowest priority. And what we have shown is that, think of the system running in some time slots. And E stands for execution, Q means that it needs the resource Q, V means it needs the resource V, okay? So EEQVE means that ran normally, made use of resource Q, made use of the resource E, sorry, Q made use of the resource V, and then E, okay? So, and likewise for the other ones. And then finally the arrival times of these tasks, these are the times at which they arrived. So that's the scenario we have in the next thing. So what we have at the beginning is L1 arrives at equal to 0, it starts running, and then it needs the resource Q. So it starts using Q. Then at t equal to 2, L2 and L3k, L3 is higher priority than other two, so it starts running. And then it needs the resource V. So it locks the resource and starts executing into that. Then, and while it's in the midst of running, at t equal to 4, L1 arrives. L1 is the highest priority task, so it gets the CPU. It ran for a couple of time units, and now it needs the resource Q. If you go back, it was EEQVE, so it needs the resource Q. But at this point, Q was already locked by L1, so L4 moves into that waiting queue. And what's the next higher priority task which is ready to run? Well, all of these three are ready to run, L3, 2, and 1. But L3 is the highest priority, so it gets the CPU back. It will continue. It was using resource V for 2 time units, so it will finish, release the resource V at time 7, then do other computation, then finish. At this point, L2 is the next highest priority task. So L2 runs, it finishes, and L1 only gets to run at t equal to 10, and then L1 finishes its use of resource Q, and the moment it gives us the resource Q, then L4 can run, and L4 does its job, and this things like that. Now the problem out here is that L1, which had grabbed the resource, is blocking L4, but I have to finish with L2 and L3 in the interim before I can do L1, so L4 faced a long wait. And the objective is, could I avoid this situation somehow? And intuition is that could we temporarily give L1 a higher priority, but one has to do these things carefully. So let's see what happens there. So there are pretty elaborate protocols which are built to manage this process, and they're referred as priority ceiling protocols. And there are many variants of them, but kind of the core concept is very, very similar. So the idea is that the priority of a task is now dynamic, and in part depends upon what resource it is using. So the idea would be, in that previous example, L1 and L4 were using the resource Q. So the idea is that Q is therefore a high priority resource because it's used by L4. And therefore, while L1 is using Q, or if L1 can use Q, then we will give it a higher priority too. So essentially, temporarily, L1 gets the priority of L4 because it is using a shared resource. That's kind of the intuition that we have. So essentially the idea is that if we have semaphores, then we attach priority with these objects also. So any resource, and basically when we say resource, deep down in the OS, there's some data structure for the radio or the sensor, and it will probably have a lock or a semaphore or mutex or something like that. So it's basically that resource. That's what we mean by resource. And the idea is that we are going to attach priorities with them, or specifically what are called as priority ceilings with them. So priority ceilings in this case of semaphores S1 and S2, which are shared by two tasks, is going to be the priority of the higher priority task, tau 1. Okay, so that's an example. So we attach priorities with resources. So in this example, what happens now is this two task example. So just to sure. task 1 locks S1, locks S2, unlocks S2, unlocks S1. And task 2 locks S2, then S1, and then reverse way. So one task uses S1, and then within S1 it uses S2, another does it the other way. And by the way, this is a classic potential problem of deadlocks also, right? I mean, what happens if task 1 locks S1, task 2 locks S2, then task 1 comes and locks S1, and now task 2 is waiting for resource S1 which is locked, and vice versa, right? So it's a deadlock situation. So you also want to prevent that as well happening. So this nested use of resources can be a problem as well. So these priority ceiling protocols attempt to manage these things. So this is what happens out here. Task 2 arrived first. It's a lower priority task. It starts running. It needs the resource S2. It goes ahead and locks the resource S2. Since it locked the resource S2, in effect, we say that its priority is bumped up, and to be that of S2. And S2's priority is that of task 1 because it's a shared thing. Later on, task 1 comes. Task 1 now attempts to use S1. Now, normally it will go ahead and lock S1, except that at this point it will say, is there anything else which has already locked a resource and is the same priority as me? And guess what? Task 2 is like that. So task 1 will not even get to lock the resource at this point. So we prevent that deadlock also. And this guy will raise the head, finish, and then so basically by attaching priorities with resources and then keeping track of these things, one can prevent both deadlock as well as the priority inversion problem that I talked about. We'll see how kind of it does very shortly. So the underlying concept out here now is that we are somehow going to attach priorities with not just tasks but resources, and tasks priorities are going to change dynamically based upon some criteria to achieve two goals: avoid deadlocks and also avoid priority inversion. So one scheme is called OCPP, original, I think maybe it's OPCP, or it's the original protocol. Okay, and basic idea out here is that each process has a priority as before, but also each resource has a ceiling value, which is the maximum priority of all the processes that can use it. So if a resource is shared between tau 1 and tau 3, then it has the priority ceiling of tau 1. And then the process's actual priority is a dynamic one, and it is the maximum of its own static priority, and any it inherits because it's using a resource which is blocked some higher priority task. So in particular, at this point, task 1 blocks because it's waiting on resource S1, and therefore task 2 will inherit task 1's priority. So if there were any intermediate tasks, task 2 will triumph them. So what the OS does is it keeps track of how these locking, unlocking events are happening, and then keeps shuffling the priorities of the tasks around. And then the final thing is a process can lock a resource only if the dynamic priority of the process is higher than the ceiling of any currently locked resource. So the idea being that this is what happened out here, that resource S2 was locked. S2's priority was the same as priority of tau 1. So when tau 1 attempted to lock S1, it would see that the OS will check, is there a resource which is already locked and whose priority is the same as that of tau 1 or higher? And if so, it will not let it proceed. So that's a preventative thing that you don't want. Even if you could lock S1, you are not going to do it because there's potential for trouble there. The net result of all of this is that if we do it this way, then any critical resource, any shared resource which is used by a lower priority task can block me only once. So so think of like there are a whole bunch of resources in the system, radio, sensors, whatnot, and let's say this high priority task uses all of them, and they're also used by some low priority task. So one thing you want to make sure is there was no repetitive blocking like this. So in this case, the scheme, it turns out, make sure that only once, the blocking will happen only once. So the overall blocking a particular task sees is kind of this expression, but let's break it down. For all the resources in the system, you can associate some amount of time it takes to use that resource by a task. So whenever that resource is used, it needs time CSK. And here I'm assuming that to use a resource, it always takes the same amount of time, and it doesn't matter which task is using it. In reality, things are a bit more complicated. Usage Ki basically refers to that is the kth resource being used by tasks which have priority greater than equal to I and priority less than I. And if that happens, then a lower priority task can block a resource and block me. So I have to worry about not only resources that I am using, but I also have to worry about blocking because there may be resources which are used by someone more higher priority than me and someone lower priority than me. Let's imagine a resource was only used by tasks which are higher priority than me. Then it doesn't matter because those tasks would have gained CPU anyway. So the challenge only comes when a resource is being used by me and a lower priority task, because that task can block me, or by a higher priority task and a lower priority task, because of our scheme, if the lower priority task uses that resource, then it will inherit the priority of the high priority task, and therefore I will get blocked. So these are the two situations where a task is getting blocked. Either it's using a resource and the lower priority task uses it and blocks me, or alternatively, I'm not using the resource, but someone higher priority than me and someone lower priority than me are both use that resource, and the lower priority one started using it, and the higher priority one came, and now the lower priority gets his priority. So temporarily now I'm seeing an interference by a lower priority task also. And the interference that I see is going to be, in the worst case, once for each one of the resources that exist in the system, because the same phenomenon can occur for every resource in the system. So if I have 100 resources, I'll have to make sure, actually I cannot take it back. In this scheme, it's a maximum. If I were to use kind of the plain priority inheritance, then it's a summation, but in this case, it's going to be the worst case resource, the resource which is most power hungry. So, most time hungry. So essentially, what this says is that I now have two sources of interference. Interference by high priority tasks and interference because of by low priority tasks, because they end up using shared resources, and this expression kind of gives me that term. So let's see how it kind of operates in practice on the same tasks that we had used before. In this example, L1 came, started running, started using Q, then L3 and L2 arrived. L3 starts running. So right now the priority of L1 is still its native priority. Its dynamic priority is the same as low priority because it has not blocked anything. So L1 starts running, then at some stage L3 starts running, and at this stage L3 wants to use a resource, wants to use the resource V. And now the check will happen. In our previous version, L3 went ahead and used V, and that was a potential risk. Here what the OS will do is it will say, okay, before I let you lock the resource V, is there a system, is there something which is going to have the higher priority because of the resource. So L1 has locked a resource whose ceiling was high. So at this stage, L3 will not proceed. Rather, L1 will get the CPU back, it will run, then L4 arrives, same game happens. At some stage, L4 attempts to tries to get the resource. Again, L1 will now inherit its dynamic priority. L1 runs, then L4 runs, and so on and so forth. What you see in this case is the following, that L4 blocked for a very small amount of time, just sufficient for L3 to do its job, and meanwhile we kept L2 and L3 sort of at a lower priority status. So we're kind of achieving our goal, and simultaneously by preventing L3 from grabbing V out here, we also prevented the possibility that what if L1 needed V here. So that would have caused the deadlock situation. So this OCPP and these kind of sealing protocols achieve these multiple goals, and they don't exist in every operating system, but they do exist in operating systems which are catering to these kind of markets. So VxWorks and all these kind of systems do have them. But so I guess the part of the message I'm also trying to give is that before you use shared resources, before you use semaphores and such, it's important to be aware of what their properties are. For example, does the OS provide priority inheritance? Does the OS provide a sealing protocol? They all are going to have different properties, and one has to, or does it provide nothing, in which case you are kind of in that problematic world. Okay, so shared resources, one has to be kind of careful. There is another version of this same protocol, of a sealing protocol, which works slightly more simply. So again, each process has a static priority. Each resource has a static sealing value. So instead of a priority sealing, now each resource has a value which is basically the maximum priority of all processes which can use. And a process has a dynamic priority which is the maximum of its own and sealing values of any resources it has locked. So essentially, the moment I lock a resource, I just get its priority. So in our example, here, the moment L4 locked Q, since Q's priority is the same as that of L4, so L1 will immediately get the priority of L4. And therefore, when L2 and L3 arrive, they will not get to run. So we kind of are more proactive about it, as opposed to waiting until things are happening. So the runtime kind of looks like this now. L1 starts using Q, L2 and L3 arrive, but it doesn't matter because L1's dynamic priority is that of L4 because it locked this. So it continues to run, then L4 runs, and kind of the thing flows this way. So in this immediate one, moment we lock, immediately we change the priority. Whereas in the original one, if we lock, we'll actually wait until some blocking action happens. So it's kind of more of a delayed action. They both provide exactly the same property. That is, blocking time is given by this maximum expression.
So I was just going to ask, in some of these diagrams, in each one of those transitions, there's always going to be that extra little sliver of the time that it takes to.
Absolutely.
And the more checks you start doing, the more you start increasing that.
Exactly, the overhead. And in fact, the reason behind ICPP is the positive thing about it, it results in fewer such transitions. Okay, because remember, it does it immediately. Okay, whereas the other one, every time some event happens while I'm locked, it will do it. So generally speaking, in fact, so this slide has that. Worst case behavior is identical. ICCP is so the second one is easier to implement because basically I don't have to keep shifting the priority much too often, and also leads to fewer context switches. But it may result in unnecessary priority movement. Okay, so that's okay. So and there are a whole bunch of I mean, this again, like when these ideas came out, obviously the way things happen in academics, a lot of improvements and all are made over the years. So a whole bunch of other work that has happened. This is kind of like the classic textbook original variant of this. Okay, so what this means is that now if I go back to that algorithm I presented at the very beginning, instead of the response time being the computation time plus the interference from higher priority task, now I also have to put in a term which is this blocking term. Okay, and that blocking term is this guy, but I still have basically the similar context, similar fixed point equation, and we solve it the same way. Of course, now I've complicated my job even more because I also have to keep track of what the resources are. If the program changes, it creates a new resource, I have to keep track of it. So the OS suddenly has become more complicated in terms of what it has to track. And the other thing is I also need to know how much time it takes to use a resource. These are non-trivial things to kind of do, but if on the other hand you are designing, I mean, if you are JPL designing NetRover, you will have to do it, otherwise the failure will happen on a different planet. Yeah, so, but the theoretic basic framework exists. There are tools and all which help you in this regard. Okay, so so that's one type of interaction between tasks, right? Via shared resources. And that concept captures a whole bunch of variety of things, right? I mean, using radios and these kind of things, obviously, but also things like when a task communicates with something, because queues or channels of communication are protected by semaphores of some form, and again, similar story applies there. Any shared data structure would be the same story. Your screen, if two tasks are sending debug messages, you want to make sure that their messages appear atomically and not kind of some character from one and some character from the other. So lots of places you are going to see the need for sharing a resource to be able to do some useful things, and so you need to protect them. Okay, so the other type of interaction that happens between tasks happens because they send data to each other. So shared resources is one, but the other one is explicitly that task 1 is sending some data to T2. So T2 cannot run until T1 produces that data. So in this case, you can think of like this whole thing is kind of like an overall program, and some event comes, initiates T1, and T2 can only run after T1 has sent it the data or T1 is finished, and likewise T3 and stuff like that. Okay, so one has to take into account these considerations also, and this kind of problem occurs in two varieties. Generally, a classic one is I have a bunch of tasks, I know their arrival times and all, and I just have to schedule it. But in kind of the embedded system context, the version is these things are happening again and again. So an event comes, starts T1, these things happen. Again, the event comes, the whole thing happens, right? So essentially what's happening is we are creating a finer structure behind each one of those tasks. An event arrives, and a group of tasks now need to run subject to these constraints, okay? And EI in this case is the execution time, is copied and pasted, and we are kind of given the deadlines. And it turns out that these kind of problems of this genre are all very hard to solve. They are all NP complete and in that category of things. So basically what you have are heuristics, various kind of heuristics that you kind of end up applying to do such scheduling. It's hard for uniprocessor. It's even harder for multiprocessor. So for example, one heuristic is as late as possible. Another heuristic is as early as possible. So you can essentially scan your graph from backward. So like I may have a deadline for T6. I'm going to go back and then say when should T6 run, and therefore when can T4 run, and so on and so forth. Or alternatively, I go forward from the point T1 arrives, what's happening. So you can imagine various kind of ways you can organize a heuristic. This slide has one of them. So basically what we do is we go backward. We schedule the last task whose deadline was the latest or farthest in the future. We put it into the interval just before its deadline. And then we look for tasks that are not scheduled. And from those, again, I look for the one which kind of feeds into the task I've already scheduled, and again, schedule them as late as possible. And after we have done this, we kind of take a pass and then squish everything for backward in time. So essentially, where the heuristic works is starts backward, schedules T6, T5, T4, T3, then T2 because it had earlier deadline had to go here, and then T1. Of course, tasks T1 arrived at T equal to 0. So what we do is then push everything backward in time because that we can always do, and the schedule looks like this, and all the deadlines are met. So heuristics like these are what gets used. There's a rich literature. These problems also occur in people who do ASIC design and all, not just in software, and kind of the methods involved are very, very similar. So in essence, what you would do is, if you, in general, you can think of your system as a cluster of such, collection of such graphs. So each graph will have an associated period because of T1. It will also have deadlines associated with each one of the constituents. And your goal is to now schedule the overall system by essentially this cluster of tasks and multiple such clusters. Each cluster would be scheduled using RM, and within each cluster, you would need to have a schedule developed according to this. So kind of RM or whatever priority-based stuff as the outer container, and then some sort of a static schedule that you develop using these heuristics as the final grain structure that you would do. Okay, so I'm going to stop out here. So there's some other kind of issues that I'm going to discuss next time related to scheduling before moving on to another topic. But hopefully, it's giving you a sense of like from that very simple model that we did last time to now we have handled some of the things that one basically encounters in real life. Even if your OS doesn't support it, it's important to be aware of them so that you can analyze and perhaps even implement them. But if for safety critical stuff and all, it does become important to use operating systems which are providing the right support, and there are obviously a lot of them which target the safety critical market. Okay, so we'll meet on Tuesday.